In lab, you guys were looking at what happens when we heated up different solids, and what we saw was that heating them up caused them to expand. It caused them to get bigger. And in fact, this is how a thermometer or many thermometers work, right? If you consider a glass thermometer, it's got a bulb down here, and then that bulb is filled with liquid, usually alcohol or mercury. When you put it on something hot, this liquid rises, and that's because these particles, when they get warmer, they expand. They expand because they move more, they vibrate more, they collide and push each other apart. And it happens in liquids, it happens in solids, it happens in gases, it happens in all our states of matter. And we're actually able to calculate how much bigger something is able to get. So it doesn't matter if we have a ball and a ring or if we have a long thin rod of metal. When we heat it up, we cause those atoms to move more and the object expands. And so in the second part of lab, you guys derived an equation, hopefully, for linear expansion. And basically, that tells us that if we have a long, thin rod of metal that has an initial length L naught, it's going to expand. It's going to get a little bit longer, so it might expand this way, it might expand this way. And its new length, L, is given by the initial length, L naught, times the change in temperature times the coefficient of linear expansion, okay, plus its initial length. Now, if we think about that coefficient of linear expansion, it tends to be a very small number and it has some funky units. Since we're getting length out of this whole term needs to multiply to be length. So what am I going to multiply length times temperature times whatever that is? Well, alpha is going to have units of per degree Celsius, or degrees Celsius to the -1. And usually these are very, very, very small, like maybe 223 times 10 to the -6th per degree Celsius. Okay, and so that tells me for each change in degrees Celsius, I'm going to get a very, very small expansion. But that can still result in a fairly long length change if we had an initial length that was fairly long. This comes into play on like a highway bridge. If you've ever driven over a highway bridge, you know the road comes in and then there's this little metal gap right here. Okay, and then the bridge continues. Well, the reason there's a metal gap between the bridge and the highway is because the metal in the bridge is going to expand and contract at a different rate than the roadway, and they don't want the bridge to buckle or sway. Railroad tracks, actually, in the super hot sun, they're supposed to be nice and parallel lines. If it gets really hot, these can actually buckle and they'll start to twist a little bit, and that can cause train derailments because they're expanding and they no longer fit between their two ends. Okay, so track maintenance and long lengths of steel, they actually have to account for the expansion and contraction of steel. Alright, so we have this equation that tells us that length is equal to, or the new length of an object is equal to its initial length times its change in temperature times the coefficient of linear expansion. Now, if you're not measuring temperature in degrees Celsius, then your coefficient of linear expansion will be in whatever temperature scale you need. But remember, since a change of 1 degree Celsius is not the same as a change of 1 degree Fahrenheit, it won't work out to be the same. You will have to find a new coefficient of linear expansion. But it's not only a linear expansion, right? If you consider a cube that has a length L naught per side, then it's going to expand in this direction, it's going to expand in this direction, and it's going to expand in this direction when it's heated. So its initial volume, V naught, is given by L naught cubed. Well, we know that the new length is given by L naught plus L naught delta T alpha, and so if I wanted to, I could figure out my new volume, which would be L cubed, is given by L naught times 1, I'm factoring out this L naught, 1 plus delta T alpha, and then I would, if I wanted this volume, okay, so cube that to get volume, I'm going to cube this side as well. Well, that gives me that volume is equal to L naught cubed, or V naught cubed, times this whole thing. Now, if we just expand that out, what I end up with is 1 cubed, which is just 1, plus 3 alpha delta T plus 3 alpha squared delta T squared plus alpha cubed delta T cubed. Okay, but remember, alpha is on the order of times 10 to the -6. And if I square that, that's times 10 to the negative 12. If I cube it, it's times 10 to the negative 18. And when that happens, these get really small. Essentially zero. Small enough compared to this term that it's actually generally ignored, which tells me v equals v naught cubed times 1 plus 3 alpha delta t gives me my new volume. Now, 3 alpha is sometimes written as beta. Okay, so what I really have is v equals v naught times beta, that's the coefficient of volume expansion, times delta t. But usually beta is approximately 3 alpha because of this math that we've done here. So if you're given the coefficient of linear expansion and you're looking for a volume expansion, you can usually just triple your linear expansion to get your volume expansion coefficient, and then the math works out the same. Oh, don't forget, that's plus v naught. So you can find a new volume if you're given the old volume and the coefficient of volume expansion, or if you know the coefficient of linear expansion, you can work out these problems as well.